Okay, so now we're going to get into a discussion of mass and volume, two very important concepts when it comes to the sciences, chemistry, physics, whatever the science endeavor is. So we're going to deal with mass first, and here I'm going to talk about the standard unit of mass according to the SI system, which is the kilogram unit. And the kilogram unit, 1 kilogram, by definition is equal to the mass of a particular platinum iridium cylinder that is kept in a vault in France, and it is related to the pound unit by this relationship seen here. 1 kilogram is equal to 2.205 pounds. Now, this is showing you the different metric units. Of course, we're combining the fundamental unit according to the metric system of mass, grams, with the different prefixes, kilo, deci, and so on. So as you can see, for example, 1 kilogram is equal to 1,000 grams, which is the same thing as 10 to the 3 grams. And we see other relationships here. So we'll be using these a lot in our calculations and conversions, etc. So as an example, we're given this problem. We are to convert 45 decigrams to grams. So the way I would start this off, of course, is that I would start off with what we're given, which is the 45 decigram. And the question is asking for the equivalent value, the equivalent value in grams. So let me write 45 decigrams here. And I would multiply by a conversion factor which relates decigrams to grams. Deci means 1/10. So therefore I would put 0.1 gram above here and 1 decigram below here. And when you work this out, you're going to get your answer as being equal to 4.5 decigrams. So this is a relatively simple example showing you how to do a conversion of that type. Very similar to what we looked at when we did conversions with regards to lengths. All right, so it's the same principle, only the different types of units are different in this case. Okay, here's another example. Now in this case, it's a bit different from the one we just did because you're given a mass of hydrogen atom which is equal to 1.674 times 10 to the minus 24 grams, and you're to convert this to ounces, the equivalent value in ounces. All right, so for this you need to, I'm quite sure, refer to the table which I would have made available to you, and you look for something giving you the relationship between grams and ounces. So I'm going to look at my copy of the table here, and according to my copy of the table, 453.59 grams is equal to 16 ounces. All right, so let me just write that up here. 453.59 grams is equal to 16 ounces, which of course 16 ounces is equal to 1 pound. So that's another relationship I'll just write here, even though we're not going to use it in this example. So the conversion factor that I would use here, I'm going to set it up such that I'm going to have 453.59 grams down here, and up here I'm going to have the 16 ounces, and I would work that out. So when I take 1.674 times 10 to the minus 24, divide that by 453.59. Okay, so the answer that I got will be equal to 3. Now in this case I would round it off to 2 decimal places, 3.7 times 10 to the minus 27. Now ounces. Now the reason why I would round it off to 2 decimal places is because if you look at this conversion factor right here, it is giving you the relationship between a metric and a non-metric unit. The non-metric unit would be the ounces, the metric unit would be the grams. And what we do in that case is that if you're given such a relationship, then you have to look at the number of sig figs here, because this is not a defined relationship. It's actually obtained by basically comparing two units. So therefore, this shows you 2 sig figs in this number. All right. This is obviously 5 sig figs. This is 4 sig figs. So therefore, you'd have to round off your answer to 2 sig figs. And that's the answer, 3.7 times 10 to the minus 27. Okay, so that's how I would do this problem. Again, it's a relatively simple problem, primarily because you're only using one conversion factor, all right? Okay, so let's move on now to volume. Now, the definition of volume is the amount of space occupied by a substance, all right? And the SI unit of volume is the meter cube or cubic meter unit. But there are other units that are also used a lot in science, namely the liter unit and the milliliter units. These are standard units of volumes that are used in most labs. And these are different instruments that are used. This is not by any means an exhaustive list, but these are the common ones that you see in most chemistry labs in schools and in academic environments and also in industry. So I just want to talk about the features of a couple of these here. This is called a graduated cylinder. As you can see, it's called graduated because you have a lot of lines here indicating the volume units, and they come in different sizes. The one that you see here is 100 mils, but you can have very small ones. I've seen a small graduated cylinder that measures 5 mils, and then you can have others that can measure up to a liter, 2 liters, and so on. The next glassware you see here is called the volumetric flask. Now, this is unlike the graduated cylinder. The volumetric flask is very accurately made. The graduated cylinder is used mainly for approximate volume readings or volume measurements, but the volumetric flask is made to measure a particular volume very accurately. All right, now this one is a 100 ml flask, and what you'll find on any volumetric flask is that there's a mark which is etched on the stem right here, which basically indicates the which basically indicates the volume measurement, in this case 100 mils. And it is so accurate, it is accurate up to 2 decimal places when the volume is expressed in mils. And for that reason, we do not subject the volumetric flask to any extremes in temperature. So therefore, we do not, for example, put it in the oven to dry, because as you all know, when any substance is heated, it expands, and when it cools, it contracts. And there's no guarantee when you heat a substance and then it cools, it contracts back to the original volume. So therefore, we do not heat volumetric flasks. If you wash it, we just hang it up to dry, and so that it can be useful for its purpose. All right. This comes in several sizes as well. The smallest I've seen is a 5 mil, but you can have, again, larger ones up to 2 liters. That's the ones I've seen. And then we have this piece of glassware, which is known as a burette. It's a long cylindrical piece of glassware which is used to measure the volume of liquid that is dispensed from it. Not to measure volumes of liquids that's in it, but the volumes of liquids that are dispensed from it. So they come in different sizes. This one is a 25 mil burette, and the way we use this is that we add liquid up to the 0 mark or close to the 0 mark. We record that volume, and then we dispense the liquid. As we dispense the liquid level inside the burette goes down until it gets to a particular volume you want. So for example, if it goes down to where the 5 mil mark is, then you know that you would have collected down here the 5 mil of the liquid that you had in the burette. So that's basically how we use the burette. And then here we have another piece of glassware. And by the way, the burettes are accurately made as well. They record typically volume readings up to 2 decimal places when expressed in milliliters. This piece of glassware is known as the pipette. The pipette is used to measure fixed volumes of liquids in particular situations. This one, as you can see, is a 10 mil pipette. Again, as in the case of the volumetric flask, you'll see a mark which is etched on the stem. That mark indicates the volume of the liquid. When you pull the liquid up to that mark, the meniscus, when it gets to that mark, then you know that you have, in this case, 10 mil or 15 mils or 25 mils. I think the largest size pipette I've ever seen is a 50 mil, pipette. So that's basically how we use this particular glassware. Typically what we do is that we suck the liquid up, not with your mouth. We use a pipette filler that we place at the top, and then we basically transfer that liquid into another vessel where there's a reaction taking place or whatever, and that's it. That's basically how we use the pipette. Now this syringe is another instrument that is used, not very often, at least not at our level, but I'm quite sure for those of you involved in the medical field, you know how to use a syringe. Basically you stick the needle into wherever you're trying to pull the liquid from, and of course you can pull the required volume of liquid into it as indicated by the scale. So these are just a couple of examples of glassware that we use to measure volumes of liquids, and there are others, but for our purposes we will be focusing on the ones that you see here. Now let's talk about some conversion examples. Now this one is a bit more complex than the ones that we have seen before, because in this case we're going from microliter to milliliters. Now you may not know, and I certainly don't, at least not off the top of my head, the direct relationship between the microliter unit and the milliliter unit. But what I do know is, based on the prefixes, if I can get this working, I know that 1 microliter is equal to 10 to the minus 6 liters, and I also know that 1 milliliter is equal to 10 to the minus 3 liters, right? So I know of these two relationships directly, all right, and I can exploit my knowledge of these two in order to carry out this conversion. So let me start off with what we're given here. We're given 4.61 times 10 to the 2 microliters, all right? Now the first thing I would do is that I would take the value expressed in milliliters and convert it to liters, since I know the direct relationship between the two, and the conversion factor I would use for that is representing what we have here. So I would put 1 microliter down here and 10 to the minus 6 liter above. So the microliter units will cancel out and I'll be left with the liter unit. And then the next conversion factor is where I would focus on converting from liters to milliliters. So down here I would put 10 to the minus 3 liters as the denominator, and 1 milliliter up top as the numerator. So take out my calculator. 4.61 times 10 to the 2 times 10 to the minus 6 divided by 10 to the minus 3, and according to my calculation this works out to be equal to 0.461 milliliters, and that's how you do that. So in this case it's a bit more complicated. You'd have to use two conversion factors in series in order to achieve that conversion. All right, so let's talk about density. So density is another important concept. It's important because it unifies two of the types of measurements we just discussed, mass and volume. And it is used to identify substances in part because densities are basically one of those physical characteristics that we use to identify substances. So the definition of density is shown here. Density is equal to mass divided by volume, all right? And of course, the units of density is dependent on what units you use for mass and volume. So if the unit of mass is in grams and the unit of volume is in milliliters, then the density can be expressed in grams per mil. And this is typically the units that we use to express the densities of solids and liquids. Because the mil unit is the same thing as a centimeter cube unit, then the density can be also expressed in terms of gram per cm cube. So what you'll find is that any density that is given in grams per mil will be the same thing numerically in grams per cm cube. If the volume is measured in liters and the density is still measured in grams, then we can express density in terms of grams per liter. And this is typically the way we express densities for gases, right? What we find is that because gases typically have a large volume compared to solids and liquids of the same mass, then it is more convenient for us to express the densities in grams per liter. And you're going to see in a table I'm going to show you how that is so. So what you'll find also is that densities varies with temperature. We all know that most substances, when the temperature increases, the volume increases, all right? Expansion takes place. So what you'll find is that for a substance like water, at 4 degrees, what you'll find is that the density is 1.0000 grams per mil, because what you'll find is that the mass is equal to 1.0000 and the volume is equal to 1.0000 mils. Now, for the same mass of water, if you were to increase the temperature from 4 degrees to 80 degrees, what you'll find is that there is an increase in the volume from 1.0000 to 1.0290 mils. And as a result of that, the density falls from 1.0000 to 0.97182 grams per mil. And this is typically what you'll see for pretty much every substance. There may be a few exceptions, but for the vast majority of substances, that's what you'll find. It is certainly true for gases. If you increase the volume of the gas, then the density will decrease as a result. And of course, what that indicates is that there's an inverse relationship, and in fact an inverse linear relationship between density and volume. Okay, so this is showing you, just to give you a picture as to the relationship between mass and volume when it comes to the densities of different substances. We have 3 substances being represented here, all right? We have water, we have sulfur, and we have gold. Each of these weigh 10 grams, right? But look at their volumes. Of these 3, the one with the greatest volume would be water, right? And that's because water has a smaller density compared to the other substances in this list right here, all right? So therefore, because water has a smaller density for the same mass, its volume would be the highest. In the cases of the diagram on the right side here, what you'll see are the 3 same substances, but they all have the same volume. And what you'll see here is that of these 3, the one with the greatest mass is gold, 19.3 grams, and that's because it has the highest density, all right? So basically what this is showing you is that the relationship between density and volume, in the case of the ones over here, is an inverse relationship, but over here it's a linear relationship between the density and mass, all right? Okay, so this is just giving you a representative list of different substances and their densities. And as you can see here, water, as I said before, at 4 degrees Celsius has a density of 1.000 grams per mil, and silver is 10.5 grams per mil, right? Mercury is 13.55 grams per mil, gold is 19.3. So that gives you an idea as to, the densities of different substances as far as the solids and liquids are concerned. And you'll notice that as far as the gases are concerned, their densities are expressed in grams per liter. As I said before, it's more convenient to express densities in grams per liter because gases occupy a larger volume for the same mass compared to solids and liquids. So therefore, we typically express the volume in liters so that, we can have more convenient numbers to work with and to, exploit when we're doing calculations and so on. Okay, so let's look at some other examples, this time dealing with densities. The first one is a relatively simple example because they gave you the volume, 13.5 mils of an unknown liquid, and they gave you also the mass. So to calculate the density, which is what the question is asking for, very simple exercise. All we have to do is remind ourselves of the equation density is equal to mass over volume, and we just put the numbers in. The density is 12.4 grams divided by the volume, which is 13.5 milliliters, and according to my calculation, 12.4 divided by 13.5, that works out to be equal to 0.92, in fact 0.919, because we have to round off to 3 sig figs, and the answer must be expressed in grams per mil. All right, because we have grams here, we have mils here. All right, so that's a relatively simple example. Now let's look at this one. This one is a bit more complex, and this is oftentimes a method used to measure the volume of an irregular object. All right, and we can use that volume, of course, to continue to calculate the density. So let's look at this question. It says a graduated cylinder is filled to the 35.0 mil mark with water. A copper nugget weighing 98.1 grams is immersed into the cylinder, and the water level rises to 46.0 mils. So the question is asking, what is the volume of the copper nugget, and also what is the density? So basically, we're talking about this situation here. We start off with a cylinder where the volume of the water in the cylinder is 35.0 mils, and then we add our copper metal to the water. The copper metal sinks to the bottom, and you'll notice that the water that is in the cylinder, its liquid level raises. And what is actually happening here in this case is that the metal is displacing a certain amount of water equal to its own volume. All right, so to find the volume of this metal, basically we take the initial volume of the water in the cylinder and subtract that from the volume registered in the cylinder after the metal has been submerged. In some textbooks they call this displacement method, the displacement method of determining the volume of an object. All right, and this only works, of course, if the substance that you're trying to determine the volume of is more dense than water. If it is more dense than water, it therefore sinks to the bottom or sinks below the water surface, and therefore you can determine what the volume is by difference. If the metal or the substance is not more dense than water, then this method would simply not work. Anyway, so we need to calculate firstly the volume of the metal. So let me do it here. So volume of metal, of copper, is equal to 46.0 mils minus 35.0 mils, and that works out to be equal to 11.0 mils. And therefore the density will be equal to the mass of the metal, which according to the question is 98.1 grams divided by the 11.0 mils. And when I do that calculation, 98.1 divided by 11.0, I got 8.92. So write it here, 8.92 grams per mil. And that's how that is done. All right, okay, so much for that example. Here is another example. In this case, they gave you the density of a certain liquid, ether, 0.714 grams per mil, and is asking what is the density, or the mass I should say, of 25.0 mils of ether. So in this case, what you can do sometimes, because density is a combined value, well, when I say combined, I mean you're combining two things, mass and volume. You can express that combined value as a conversion factor, and that is very convenient for what we're about to do. So what I'm going to do here is start off with the 25.0 mils, and what I'm going to do is express the density as a conversion factor. Right now the density is 0.714 grams per mil. So the way I would express it here is that I would put 1 mil here, and I would put 0.714 grams above as a numerator. And that's it. All I have to do is compute on my calculator times 0.714, and the answer I got when rounded off to 3 sig figs would be 17.9 grams. In fact, 18.0 grams. I'm sorry. This should be 18.0 grams. All right. So that's how I would do that. Okay. Here's another one. Question says the density of oxygen at 0 degrees Celsius is 1.429 grams per liter. What is the volume of 32.0 grams of oxygen at this temperature? Again, it is convenient to use the density as a conversion factor for a problem of this type. So I'm going to start off with the 32.00 grams of oxygen, and I would multiply that by 1 liter above, 1 liter, and down here I would put 32.00 grams below, and I would do my thing on my calculator. I'm sorry, this should be 1.429. I'm sorry, this should be, let me scratch that out, 1.429 grams below. All right. And then I'll do my thing on my calculator, 32.00 divided by 1.429, and this will work out to be equal to, now in this case I'd have to round off to 4 sig figs, so this works out to be 22.39 liters. All right. Okay, so that's basically how I would do that. All right, so let me see here. Okay, so that's it for today, for this video. So the next video, I'll be discussing temperature as a concept. All right, until next time.